Hello, this is uh, Denver McMurray, and I'm here for our first lecture, which is about Chapter 1, about science. Science, to start with, the word science literally means to know. Okay, you may be familiar with the word conscience, which is basically conscience. It means with knowledge. If you do something against your conscience, you know it's wrong, but you go ahead and do it anyhow. Okay, and so science has to do with what we know. All right. Now, question. The idea if science was originally, instead of opinions or just discussing and arguing about things, that we could come up with a way to know that something is correct or not. All right. And we'll talk more about it in a minute. But Galileo was one of the first people who's credited with starting what we call the scientific method. And that's kind of the process or steps by which we try to go to know something, to know that it's true. It's not just what I think or what you think, but that there's actually some kind of proof behind it. Science is intended to be a rational thinking, critical thinking, problem solving, finding the cause and effect for different things, uh, trying to explain basically the world around us, what it amounts to. Now, in science, though, there is what I can call the percent of certainty. There are some things, laws, for example, that we are pretty much dead sure on. Gravity, if I throw something into the air, I know and can calculate how fast it will go up and slow down and then eventually begin to fall back toward the ground and how fast it will speed up as it comes back down. That's pretty much certainty. Okay, we're pretty close to 100%. Could we find out something different or find some special circumstances in which gravity doesn't operates differently than what we have here on Earth? Certainly. But pretty much gravity is going to function the way gravity functions, and we have a very high certainty of that. Now, other areas we may not have as much. For example, in geology, when you're talking about fossils, you're talking about a very small percentage of the animals that were alive. That what is preserved is usually teeth, bones, harder parts, very little of the organs and tissues of that sort, muscles and so forth. So we really know very little about those animals, and we only have a few remains of a few of the animals that were alive at that time. Okay, and so obviously your percent of certainty, if we want to describe what life was like at a certain time period, uh, we don't have as much to go on. We know a little bit about what kind of animals were there, what kind of plants were there, and we can use other things to come up with evidence, but obviously there's never going to be the same type of evidence as we have for, say, something like gravity that we can test and analyze and do a lot more concrete test on. And so there's a lot higher certainty for some things. For example, climate change. That the fact that there is global warming is a fact. Okay, that's 100% certainty. Now, what extent have we increased that? What will the effects of that be in the future? That may be more debatable, and we'll just have to see. But there's certainly a lot of evidence, but people are not uniformly agreed on what that evidence means. So, but don't confuse part of it, that fact, for example, that there is global warming. The global climate is going up right now. Okay, how much of that is due to man-made interference? How much of that is caused by natural fluctuation in the cycle and so forth? That might be a little more debatable. All right, so there's always a certain degree of certainty about things that we know in science, and we're always adding to that knowledge. We're always changing it as new facts, more information becomes available. We're always changing what we know. It's always a good idea to change if you're wrong. If you're right, then it's a good thing to not ever change your mind. All right, but obviously if you're wrong, then not. All right, now, anytime science has come along, usually it's at the bring up new ideas, and there has always been opposition to new ideas. In your textbook, it points out a lot of times that religion and science have been opposed to each other. In particular, the Catholic Church, which was the church at that time, took, for example, about the Earth being at the center of the universe, which was believed for a long time, and it was held that no, everything revolved around the Earth. Well, it turned out Copernicus said no, he thought the Earth revolved around the sun, and Galileo, about 200 years later, came and did a lot of experiments and measurements of the stars and so forth, and came up with more proof that really substantiated the fact that no, instead of everything revolving around the Earth and everything else revolved around the sun. And so there was a lot of opposition to that for religious reasons, but religion and science are not always opposed, or nor do they have to be. I think very few people now obviously would think the fact that the sun, everything revolves around the sun, affect their religious beliefs, okay, or shake any of that. But at that time, it was believed by society in that time and the religious leaders at that time that could not be true. On the other hand, it should be pointed out many of the early scientists were in fact very religious people as well. So they're not necessarily opposed. I think it's probably more fair to say that new ideas are often opposed by religion, but they're also opposed by other scientists. Many scientists came up with ideas, particularly if they were fairly revolutionary for their times, and were practically rejected, even though later, very oftentimes after that person died, they were found to be, yes, they were in fact correct, but they were kind of way ahead of their time, and so they were rejected by scientists or society. At one time, taking baths was not accepted by society and considered kind of an outlandish idea. So things change over time, and generally any new idea that science comes up with a lot of times is rejected originally. Now, some people have taken that fact and used the fact that everybody rejects what they say, as evidence that, say, they're just ahead of their time. And so you will see a lot of what we call pseudoscience, astrology, a lot of health food fads that come and go, and so forth. And in the pseudoscience they say this is science. When they say, oh, well, all the scientists mock us and look down on us because we're revolutionary and we're ahead of our time. And in fact, they really don't have much proof to back up their claims. So one has to be very careful when you're evaluating, for example, diet and health food ads, various things like this, because they're saying, well, it's just revolutionary and we're ahead of our time and that's why no one accepts us. But you need to look at their evidence. Do they really have evidence? Have they proven what they're saying is true or not? Okay. All right. But there is always opposition to new ideas, very often. But it's not limited to just religion. It can also be other scientists or society in general if they're just not ready for that idea yet. All right, the last thing I'd like to talk about in this lecture, or another thing, we'll see how many more things we have time for. Causation versus correlation. This can be very deceiving sometimes when we're trying to prove something, and things like pseudoscience can take advantage of this sometimes. Sometimes there's a correlation, but not necessarily a causation. Correlation just means that there's a connection or a relationship between two different factors. Okay, when this one happens, if this one over here does something also. Okay, and if it's a positive correlation, that means, for example, if this increases, say, the number of cell phones, then the number, let's just say, ear cancers increases over here. Okay, so they both increase. That's a positive correlation. Or they can be what we call a negative correlation. We can say if the more and more cell phones there are, the less and less ear cancers, say, that there are. Okay, that would be a correlation. In other words, when one changes, the other changes. So they are related to each other. There's some kind of connection. However, that does not necessarily prove that one of them causes the other. Okay, and so in medical research and health research in particular, we have to go back and really actually prove that a certain factor causes that. Or, there might be other reasons that, well, people that have more cell phones may also have other things in their life that actually would cause them to be more likely to get cancer. Okay, so causation means that we've actually proved that something causes a disease. So, for example, cell phones, there are no accepted studies that have really shown a correlation between, say, cell phones and cancer. All right. But on the other hand, cigarette smoking, tobacco products have, okay, and have been proven to cause that. Although for many years in the 60s and 70s and 80s, the tobacco companies had their own scientists that performed many experiments, and they maintained for a long time that there was no causation between tobacco and different types of cancer. But eventually, the evidence became overwhelming, and they have finally kind of reversed their mind on that. All right. So, let's talk about the scientific method then for a second. We have a little bit of time before my thing goes out. We talk about the scientific method. We're normally thinking about a set of steps you probably learned in school, starting sometime really, really early. Scientific method. We think of, you start with a problem or something you're curious about. You come up with an educated guess or a hypothesis. Okay, and a hypothesis is what you think will be the answer. You say, when I do this, I think this will happen. All right. And then it has to be testable. Very hypothesis is a very important thing, because if something's not testable, then it's not something that can be proven scientifically one way or another. For example, if I said the best type of music is country and western music, okay, is that testable? Is that hypothesis testable? Not really, because unless you pick some sort of standard to measure it by, because how do you decide what's good music, what's the best music? Everybody's really more of a matter of opinion, so it's been very difficult to test that. Okay, so we would say that's not a scientific question. Now we could do sociology type thing, where we could say, well, we could say it's the most popular type of music, and we take a survey of the people that we're talking about in a certain town or certain area, and see which one is the most popular. Or you could measure it by certain, which one's the highest pitch or the loudest, or whatever you want to do. If you set some sort of measurable thing, standard, then we could probably measure that. But in general, we couldn't say that which type is the best kind of music, because that's just not something that we can really test. And so in order for something to be a scientific statement, it has to be something that can be tested. All right. For example, there are alien beings that are around us that are undetectable by us. Well, we can't test that, because we just said they're undetectable, so we wouldn't know if they were there or not. So we really can't test that. Okay. Then if you had a hypothesis, say I thought that if I added fertilizer to my tomato plants, they would grow better. Then I could do an experiment. I could get tomato plants and I could test them, and I could see did they grow better or did they not grow better with more fertilizer. Okay. Now, in order to do that, I would have to have two groups. I would have to have the control group. The control group would be the one that is being grown without fertilizer, and I would have a second group that I would have with fertilizer. And then I would measure the results of each plant. I could measure their plant height. With tomatoes, I would think you'd really be more worried about the number of tomatoes and perhaps the size of the tomatoes that were being produced. And then I could compare those two groups and see which one actually helped. But it's very important to have the control group, because if I just have a group of tomatoes with fertilizer, and yes, they get really tall and they put on lots of tomatoes, but if I don't know how much they would have produced without the fertilizer, I really don't have a basis of comparison to say that, yes, this really did help. Okay, then we could analyze the data, sometimes involve charts and so forth, and eventually we could come to our conclusion. Yes, it did help to add the fertilizer, or no, it did not help. Okay, and that's basically the steps of the scientific method. Now, just for the real world, it's not always that pretty. A lot of scientific breakthroughs have come just by accident. Styrofoam was invented by a froth on a plastic chemical that someone was making. They threw the froth off, flopped it off to the side, kept foaming up as they were trying to make the styrofoam, the hard plastic. And then later they found the stuff that they had plopped off on the desk and said, hey, this is kind of neat foamy stuff. It's kind of like a sponge. And therefore, eventually they made styrofoam from that. So a lot of times it's more by accident or serendipity, and that can happen sometimes. All right. The last thing is repeatability. An experiment must be repeatable. If I do an experiment and get certain results, but someone else does the same experiment, follows my instructions to the letter, but they can't get the same results, then something must be wrong. Either something else affected it that I didn't explain when I said how I did the experiment the first time, or maybe they're not doing it right. But in order for an experiment to be considered valid, you should be able to do it over and over again and get the same result each time. And other people should be able to try it and get the same thing over and over. If not, then you have to kind of wonder if it's actually accurate or not. All right, so that's it for the scientific method. We'll part one of the notes, and we will go on to part two. I'll see you there.